final portion of Unit 12, Lesson 1. This is going to focus on what is E, which is the base of the natural log, or it's a number, it's a constant, it's a mathematical constant. We're going to look at it, it's also called Euler's constant, and we're going to look at why it's important. Prior to watching this video, you should have watched the YouTube video that I have as a link that goes through and it describes it using compounding continuous interest. It does a great job of showing how it grows. Of course, E is more than just any number. It is one of the most useful mathematical constants. If you graph the equation y equals e to the x, you're going to find that the slope of that curve, here's that curve, at any given point is also e to the x, and that the area under the curve from negative infinity all the way up to that point is e to the x. It's a strange coincidence, but E is the only number in all of mathematics that can be plugged into the equation y equals n raised to the x, for which this pattern remains true. The slope at this point, which is the tangent line at that point, is e to the x, and the area is e. Okay? Now, in calculus, which is all about finding slopes and areas, you can imagine that E is a pretty important number. It's also an important number in physics, where it shows up in equations for waves, such as light waves and sound waves, and quantum physics. So, again, if you've watched this video, the video that I put in there is your first item. It's going to go through and it's really going to show it to you when you compound interest continuously in a bank, which is really at this point in time in your mathematical career, the application that makes the most sense. Those of you that move on to physics, especially calculus-based physics, and get into calculus, you'll do a lot more with E. Now, this particular video, which I also put out there, is just for fun. It's when E and pi meet and go on a date. So it's just another introduction to E. It has some tongue-in-cheek humor, some puns, things like that. Feel free to watch that if you want. It's just funny, or it can be. Moving on, the natural base E. The natural base E is irrational. That means it does not repeat and it does not end. It's defined as 1 plus 1 over n, that quantity raised to the n as n approaches infinity. And E approaches the number 2.71828. Bottom line, using E, okay, you use E instead of this, right? And it makes equations much simpler to handle. E is used in a lot of applications, including the estimation of ages of artifacts found at archaeological digs and the computation of interest compounded continuously. Again, E's a mathematical constant. Using E as opposed to 1 plus 1 over n raised to the n as n approaches infinity, it's just makes equations much simpler to look at, much simpler to work with. Now, E, while it is irrational, it's a real number. So you treat it just like any other real number. E squared times e to the 6th. Well, if you are multiplying like bases, that means you add the exponents. So 2 plus 6 means I have e to the 8th. Division. When you divide like bases, you subtract exponents. Now, 6 divided by 2 is still 3. Okay, when we're dividing numbers, we still divide numbers. So don't do subtraction here. This is 6 divided by 2. That gives you your 3. E to the 4th divided by e cubed. That's where we do the 4 minus 3, leaves us with just e to the 1 or e. Negative 4, e to the 3x, all to the 2. I'm going to take the 2, and I'm going to raise the e to the 3x. I'm going to square that, and I'm going to square the negative 4. So that means I'm going to have negative 4 quantity squared, and then e to the 3x squared. Negative 4 quantity squared is negative 4 times negative 4 is 16. E to the 3x squared means I have e to the 3x times e to the 3x. I multiply these exponents and I get e to the 6x. Okay, pause the video for a moment and try these last two. Did you get E? And did you get 3e to the 5th? Okay, remember first here you have to cube the negative 3. So negative 3 times negative 3. Negative 3 times negative 3 is positive 9, but you've got to cube it. So you do another times negative 3, and that's where you get your negative 27. Raising a power to a power means you multiply, so it's e to the 12th. The denominator, you don't do anything. Now, negative 27 divided by negative 9 is 3. 12 minus 7 is 5. When you're doing this on the calculator and you need to evaluate e raised to a power, okay, that is nothing more than using your calculator, and whatever calculator you have, if it's a scientific calculator better, you're going to have a natural log button. So locate the natural log button, and typically right above it you'll see an e raised to the x. On the TI-84 it's e raised to the x. So if I want e to the negative 3, I put in second natural log and then just negative 3 and hit enter. Now all of these answers here, I rounded these to the nearest thousandth or to the nearest third decimal place. So because the fourth one out is a 7, that would round this up to 0, 5, so 0.050. Boom. Right. The rest of these, second natural log gives me my e to the x, 0.7, and I hit enter. 2.014. Okay, try these last two. It's not hard, it's very simple, but it's knowing that this button exists on your calculator and where to find it. So try these two. Did you wind up with 2.484 and 0.135? Again, rounding to the nearest thousand. Great. If you need to go back, pause the video and just double check and make sure that you use the negative and not the subtraction sign, because if you use the subtraction sign, the calculator will give you an error. Okay, graphing natural base functions. I'm not going to get into a lot of this because it's basically the same as everything else. You're going to use transformations. I've got a vertical stretch of 3, horizontal stretch of 0.4. Essentially, I'm going to put in a couple of points. I look at this and I know I have a positive exponent, so it's growth. I did not raise it or lower it, so y equals 0 is my horizontal asymptote. So I simply plug in 0, and I get out 3, because e to the 0 power is 1 times 3 is 3. Then I can plug in a 1, and I get 4.48. Great. I do an approximately 4.5, and then I just do the curve. That's it. You should be able to describe the transformation. Tell me where the asymptote is, and then plug a couple of values in and plot those values. Here's what the equation looks like. Okay. A is your vertical stretch or compress. E is your constant number. The plus or the minus reflects it over the y-axis, and again, A, if it's negative, reflects it over the x. H moves it left or right, K moves it up or down. That's it. A positive exponent, we have growth. It goes up left to right. Decay, negative. It's decay, down left to right. Now, it's just a couple of pictures. This is going to be down left to right. It's going to move to the left 3, and it's going to go down 2. So I know my horizontal asymptote is y equals negative 2. So I simply go left 3, down 2. Here's my horizontal asymptote. Boom. Draw my curve. Positive growth. Again, I moved it up 1. So since I moved it up 1, I'm going to have my horizontal asymptote. Oops, will be at y equals 1. Boom. That's this guy right here. And then I've got my curve. If I plug a 0 in, anything to the 0 power is 1, so it's 1 above it. And then I can plug in a 1 if I want and get an approximate point and draw my curve. That's all there is to it. Now, Looking at an application, continuously compounding interest, they have this special little equation called PERT. Your future amount is equal to your current amount times E raised to the RT, where R is your interest rate as a decimal, and T is your time in years, because R is your annual interest rate. So if you deposit $1,400 in an account that pays 4% annual interest, compounded continuously, what is the balance after 1 year? Well, I put the $1,400 in for P. E is a constant. 4% is 0.04 times 1 year. Plug it into the calculator. How is that different than just 4% interest? Well, remember, 4% interest would be, I have $1,400 that I deposited, and I'm going to add to that 4% of, so it's multiplying 1,400, and I'm going to get $1,456. So compounding it continuously gave me an extra $1.14. And you might go, huh, who cares? That starts adding up when you start talking about you have $100, or you have 14,000 or 140,000. That amount starts getting bigger and bigger. And when you start compounding continuously over continuous interest, it grows quickly. Let's try this second one here. You deposit $800 in an account that pays 9% annual interest, compounded continuously. What is the balance after 3 years? Again, here's your original deposit, your interest rate, your annual interest rate as a decimal, and the number of years. You wind up with $1,047.97. If you did this out, if you did 800 plus 800 times 0.09, after the first year, you'd have 872. You do this for the next year and the next year, you wind up $10 more. Again, not a lot, but $800 isn't a huge amount, okay? But you still wind up with a bit more than you had, and you keep getting interest on your interest. So it grows fast. Just the summary? Okay. Exponential functions are of the form y equals a, b, where b is some number raised to the x minus h plus k, where b is greater than 0, and b does not equal 1. B can't equal 1 because 1 raised to any power is 1, so you wind up with a horizontal line. The domain of exponential functions is all real numbers. The range is y equals k. Basically, it's y equals 0 unless you move it up or down. If 0 is less than b is less than 1, the function is decreasing. Okay, or if you have a negative exponent, it's decreasing and it's called decay. If the base is greater than 1 or is increasing, then it's called growth. The y-intercept of b raised to the x is 1 because anything raised to the 0 power is 1. The graph of the parent function does not intersect the y-axis. Notice I said the parent function, not of just any function. There is no x-intercept for the parent function. The line y equals 0 is the horizontal asymptote of the parent function. Y equals k is the asymptote if there's a vertical shift. The function is continuous. I can put my pen or pencil down and draw it without ever lifting it up. When we get to solving basic exponential functions, you determine like bases, rewrite the function using like bases. Then, since the bases are equal, the exponents are equal, so you just set the exponents equal to one another and solve for the variable. Are you done yet? For this lesson, you're done.